Good day everyone. Today we are going to take a model for the sum of n terms of a geometric progression. We first try to see what a geometric progression is. We saw an arithmetic progression in which we start with a number and keep adding the same number, which we call d. Here we start with a number and keep multiplying it by a same number. Here we are multiplying by r, so a into ar into ar, that means ar square and so on. That is how we get the terms. Now what will be the nth term here? We are interested in n terms. The first has no r, second has r raised to 1, third has r raised to 2, the last should have r raised to n minus 1 because that is going to be the nth term. Now this is the general form. What we can do is we can take a common and consider only 1 plus r square plus r raised to n minus 1. If we can add this up, then a is common, so you multiply by a, you get the answer for the general one. So we shall be trying to get a model for this. Now the result is, of course, I write it down here. It is 1 minus r raised to n upon 1 minus r. Here, if we take r greater than 1, you can see that if you take, say, 2 raised to 3, 4, 5, it will get larger and larger, and it will be r raised to n minus 1 upon r minus 1, but it will be a very large number. We are interested, therefore, in r being between 0 and 1, and we note that when r is between 0 and 1 and you take the powers, r, say 1/2, then you take r square, so 1/2 square will be 1/4, 1/2 cube will be 1/8, it will get smaller and smaller. So since r is less than 1, the powers, when you increase, the number will get smaller and smaller. Okay, that much with the formula. We are interested in showing this with the help of a model. In fact, there are many models which they are called proof without words. For infinite sum, not n going to infinity. And in particular cases, there was no such model for this. I looked at the internet. We did not work out any with Rao-Sahib also. But then I was reminded that Rao-Sahib once gave a geometrical proof of this result. And that inspired me to make up this model, and this is the result. So here is the model. Now in this model, I've drawn the figure here because I would not like to write anything on the model, and it will be better if we can write here and see. So what we have done is, along a line, along this line, we have taken 1 r. Now we have this. So we know what r is, we know what r square is, we mark all that. In between there will be many more. There will be many more here. And the last will be r raised to n minus, this length will be r raised to n minus 1. Okay. What we have done now is that this is a 1 by 1 square. From this length 1, we have r. We take away r. And what we shall be left with is, of course, 1 minus r, which we don't want just now, but anyway. Now this point and this point we have joined and formed a triangle to meet our baseline. And that is what you see here in the model. This is 1, 1, 1. R square, r cube, and so on. This will be r raised to n minus 1. Now, one thing that we would like to check here is that we have already taken here r and r. We don't know how much this is, but this will show you. See, this is 1 r square, this was r, and this is also the same. So these two are the same. Naturally, we have taken it that way. What about this now? This was r. Now this is r square. This is r square here, and you can see that it is the same as that, as the height. Or in other words, this will be r square. Then we take the next one. This is r cube, and we can check that it's the same as the height here. So this is r cube, this is r cube. Or in other words, if you have r here, the height preceding it is the same. The height preceding this will be r square, this will be r cube, and therefore if the last one here is rn raised to n minus 1, the last one here will be r raised to n minus 1. But we have all those here now. But we would also be interested in the last one. This last height here, or in other words, the last height here. This last height here, how much would that be? Well, that should be, this is the same as this. So this should be the same as the next one. What would be the next one here? We don't have it, but what should it be? It should be r raised to n. And therefore, this length will be r raised to n. Because the next one here would be r raised to n. So the previous height will be r raised to n. Okay. Now, we don't need all this. We wanted just to check that these are the previous heights. So that it has done its job. Now what we want to do is, with the help of this model, we want to show this. Now what does this mean? This is Sn into 1 minus r equal to 1 minus r raised to n. This is what we want to prove. Why did I write a bracket here? Because we want it in the form of a rectangle. Well, we'll put it as 1 into, because we have 1 here. Okay, this is what we shall try to prove. So now we have to look for, in the model, for rectangles whose sides are Sn and 1 minus r. Let us see. We have seen already that this is 1 minus r. Or in other words, this length is 1 minus r. How much is this? Well, we have taken exactly up to here. Up to here. 1 plus r raised to n minus 1, and that is our Sn. So this length is nothing else but Sn. So we have taken Sn up to here, and so this is Sn. This is also Sn. They are all parallel to each other. They are all Sn. So we have found out Sn already. But we want a rectangle whose other side is 1 minus r. Here is 1 minus r. This is 1 minus r. So this is Sn into 1 minus r is the whole upper rectangular strip. So that takes care of the left hand side. Now the right hand side is 1. Here is 1. Here is 1. We can take either one. But the other side has to be 1 minus r raised to n. Now what about that? R raised to n is right here, where we stopped our Sn, or in other words, it is here. This last thing is Rn. We don't want it. We want only up to 1 minus r raised to n. So we want to remove this part below the red line. So we do this. This r raised to n, the last height, we are removing. And we shall consider only this upper rectangle. Why? Because now you have 1 minus r raised to n. Up to this view, you have 1 minus r raised to n. This is 1, and that takes care of the right hand side. In other words, we now want to prove that the rectangular strip at the top and the rectangle on the left have equal areas. Then we are done. Okay, for that purpose, we note first that this rectangle, this triangle and this triangle, they are the same, right? these two triangles are the same, and therefore this black line here, it divides our rectangle into two equal parts. Okay, now in these two equal parts, we have these two triangles which are equal. I'll show after I have fixed them. These two equal triangles I have fixed here. They are equal area. Similarly, these two are equal. Okay. Now we wanted to prove, if you recall, that the upper rectangular strip and this rectangle on the left have equal areas. We also noted that if you look at this, the triangle below and the triangle above had equal areas. They were both equal to this. Now from this equal areas, one below the diagonal, one above the diagonal, take away small blues, one small blue and one big blue. From the upper rectangle, if you take away this and that, you will be left with this little strip here. It is a part of the whole strip that we wanted. In fact, it is this much less. Well, okay. In the lower triangle now, take away the same thing. One small triangle and one big triangle, blue one, and we shall be left with this rectangle. And as you can see that if we add this to both, the first will be the top rectangle, which is Sn into 1 minus r. The second one will be this one, which is 1 into 1 minus r raised to n. And that finishes with the verification. Now, as I told you, there are many models for infinite. Oh, by the way, we can, with the same model, the result for infinite sum can also be proved. I will just show you and leave it to you. It can be done like this. Now infinite sum means r goes all the way here, up to here. So this part which we have not considered, we must consider, and we must take our rectangle all the way here. This will go all the way, this will go all the way, and we will have bigger rectangles. This one, whose length will be the whole sum to infinity, will be s into 1. And this will be s into 1 minus r. Do it exactly like this with, after taking out this strip. Don't take away this 1 minus r raised to n and consider the whole rectangle, and you should do it. Well, okay. Now the second one was, I was talking about the infinite series, infinite sum, and that is given in many places as word without proof. And you will see that it is really word without proof, because here is a triangle which we shall take as 1 unit. Now we know in the midpoint theorem, if these two are the midpoints, we know that if these two are the midpoints, then the four triangles will be congruent. Or in other words, the black one is 1/4 of the whole unit. Now consider this part and take its midpoints, then the black triangle, forget about this, the black triangle will be 1/4 of the whole, but the whole itself is 1/4. So the first piece was 1/4, The second piece of is 1/4 of 1/4 is 1/4 square, and then you can continue. This one will be 1/4 of the upper part, which is this much part, and that will be 1/4 raised to 3, and so on. And when you take all the way to infinity, you will reach the vertex, hopefully. Now, how much is this? This is all, as you saw, the black portion. So when we add up all the black part, we should get the sum of the series. But how much is this? Well, look at this part. Of the whole strip, this is the 1/3. Then you look at this part. Of the whole strip, this is 1/3. Of the whole strip, this is 1/3. Of the whole strip, this is 1/3. This will continue. And every time, the black part will be 1/3 of the corresponding piece between the parallel lines. When you add it up, it will be 1/3 of this, 1/3 of this, 1/3 of this, and in short, the whole thing will be 1/3 of the whole. So this will be equal to 1/3. This is called proof without words, because you don't really have to explain all this, although I did. This is 1/4, 1/4, 1/4, 1/4 of each. And if you take it horizontally, it is 1/3, 1/3, and so on. So this is 1/4 of the whole, 1/4 of 1/4, 1/4 of 1/4, and so on, giving left hand side, and 1/3 plus 1/3 plus giving the right hand side. Well, okay. Thank you.